Epic. Epic! Epic Stat Tool 1 speedruns of statistics! Brian Stevens! Versus Chapter 17, comparing means for independent samples. Begin!
Hey everybody, we are back right here. Let's see if people can see me. I think the last video didn't go through to the stream, so I'm gonna have to reset that. I think everyone can see me right now. So say hey in the chat if you're here, but I think the last video connected to the previous one, so I'll have to reset that. I have to take more moments between the stream or it starts to reconnect it to the previous stream. It does say 4 people are watching, which is good. Say hey in the chat, we're doing Stats 1 speedruns, and we can talk more later. So we're doing some Stats 1 speedruns. We've gone all the way up to chapter 17. I'll have to, hey, Ashura, good to see you back right here. Sorry about that last video, and I couldn't see the chat because I was in the wrong chat. So I was like, no one's chatting. And then I was like, well, so people were watching and following along, it seems. Some people were watching, so we're getting the next speedrun going. Good to see you here, Nick. And there's chapter 17. So we're going to speedrun chapter 17. I'll have to cut that video and reassign it and remake it, but I'll relabel that video. Yeah, chapter 16 we just did. It's connected to chapter 15. So if you're watching this right here, I'm gonna have to relabel the videos after this, but because I started the stream too soon, it connected back to the old stream and I was streaming through the same stream. So I deleted that video because I deleted the old video, like I deleted the spot I had placed for it. So I need to not stream for like 2-3 minutes between streams, not like go to the next stream immediately, or it literally starts re-uploading to the previous stream. You learn something new every day. So sorry about that. It is connected to the old video. So check out the previous video for chapter 14, which currently has chapter 15 that has chapter 16 on it. I should be email me the questions or Discord me the questions. I got to log back onto Discord. I'm doing all the Stat 1 right now. So you're asking about sigmoidal. The sigmoidal shape, well, we figure out the estimates via the maximum likelihood estimates. I saw your question in the chat as I was loading this up right here. The maximum likelihood estimates are created via the logistic curve, and then we figure out sigmoidal up if it's positive or sigmoidal down if it's negative. Hey, let's start doing some Stat 1. Put those questions in the chat, and we're gonna try to do some more 320. I should be able to do some 320 probably tomorrow. I'm gonna do some 320 coverage. So stay tuned. Here we go. Let's talk some Stat 1. Boom. We're starting the speedrun right here. Understand, you're welcome, Nick. Understand the parameter of a difference of 2 sample means right here. So what's going on right here? What's the deal with these 2 sample means? Tried to move the timer on my screen. What's the deal with these 2 sample means? The 2 sample means right here are mean 1 and mean 2. So it's important to know that we're talking about here 2 groups. Well, the 2 groups would be something like the average GPA of UT students. So that would be like mu UT. And this would be, we're trying to estimate the true difference of UT students' GPAs versus Florida students' GPAs. Now, what you'll notice here is when we do this chapter, we're analyzing here a quantitative Y and a categorical X, because you've really got here group 1 and group 2. I'm just gonna call them A and B for the moment. And you're gonna analyze the difference between the 2 means. Now, these are box plots, which don't show means, but you can use box plots to kind of view the distributions. And we do have what appears to be a large difference. You can put means in here sometimes as stars or dots, and you could look at the difference between the 2 means. That's what this chapter is trying to analyze right here, is the difference between the 2 means. And so we're analyzing just, is there a difference? Is there not a difference? When we think about what do we mean by independent samples, well, we're saying that one group does not impact the other group. So independent samples right here is group 1 does not impact group 2. And what does that mean? Well, if we have UT students' GPAs and Florida students' GPAs, then a student at UT's GPA would not be directly impacting a Florida student's GPAs. I like to talk about when we have dependent samples. A dependent sample would be something like this. What if we were to look at your Stats 1 knowledge before you took the class and after you took the class? Some people come into Stats 1 having taken statistics like in high school, or maybe they, just learned some statistics along the way through science classes. So someone who comes in with knowledge would be more likely to have knowledge after the class. And someone who starts without any knowledge would, they could have as much knowledge. But think about it. The knowledge you have at the end of class is going to depend on the knowledge you had at the start of class. You can still learn everything, but there's going to be a dependency. Like those who had AP stats are probably more likely to have more knowledge because they came in with more knowledge. So when we think about this right here, we have independent is when knowing the mean for the first group, like if you know UT students and Florida students' GPAs, they would tell you nothing about each other. But we have dependent, where we can say like someone's knowledge at the start of the class would depend, or someone's knowledge at the end of the class would depend on their knowledge at the start of the class. So dependent means is not what we're covering here. We want independent groups right here, independent groups. Conditions to check when comparing means, some classic stuff right here. We got to hit the button. You know what's happening. So condition 1 is random. That means we randomly select each of the observations. So we want to randomly select UT students. We want to randomly select Florida students. 10% means we select less than 10% of UT students. We select less than 10% of Florida students. And then the nearly normal condition. I have much longer videos on this, but I've mentioned it a few times. This is when we either look at the shape of the distribution to see if we have a large enough sample size. We look at the normal probability plot to see if it's straight, or we look at the p-value for the goodness of fit test. Once again, we do not look at bar charts. I cannot say that enough. Bar charts are for categorical data. We're analyzing a quantitative y right here. That's what we're talking about. The last condition right here, condition number 4, as I call it, is going to be that the groups are independent of each other. And that's what we're talking about with the independent means. So condition 1 and condition 2 are always the same. That's why I'm always like condition 1, random. Condition 2, less than 10%. Condition 3, because it's quantitative, we're going to do the nearly normal condition. And condition 4, because there's two means, the two means need to be independent of each other. Now we get into some of the calculations. So now we're going to talk about the standard error for the difference of the sample means and the relationship it has to the standard deviations. The standard error is basically just variation between the means. Let's go ahead and write it down right here. Well, first, let's look at a standard deviation, which is just S. To calculate the standard error for the difference between the means, we take each one of these, we take S sub 1, which is the standard deviation for the first group, and square it. Then we divide by N sub 1, which is the sample size for the first group. We add this to S sub 2, which is the standard deviation for the second group, square that, and divide it by the sample size for the second group. Then you square root it. Now, the whole reason for this, let's look at what it kind of looks like, is if you think from previous chapters, you were using things like S over square root of N. So when you do S over square root of N, if you were to square this, you would get something like S squared over N, but you can't just square things. You have to unsquare it. You have to square root it. So now those are equal, but look at this. This is what we're doing up here, but we're doing it with two groups. So you don't have to memorize it. We do give it to you on the formula sheet, but just understanding how when you have one group, you're doing S over square root of N, but you can't just, if we square it, we want to unsquare it, we want to square root it. So all of this right here, let's just take the square off of this because we do want them to be equal. These are now equal right here because we squared it and then we square rooted it. So this is still just the same thing as this. So that's a big explanation to say this is the standard error for the difference between two means. So this is the standard error right here, and we're going to be using it here in just a moment. I wish I could decrease. Oh, is it really that one thing? There we go. I think weird things happen. So here, let's go ahead and take a look at this and continue on. The degrees of freedom calculation. If Mubot is awake, which is he currently in our chat? He is in our chat. Mubot is here. Thank you, Mubot. Let's go get the T degrees of freedom calculator. The degrees of freedom for this one is a complicated formula. We will not have you calculate this degrees of freedom by hand. It is given to you in jump output. So we'll look at some jump output here in a second. Mubot's going to help out with the link here. I could just copy that. Hey, Mubot's giving us the link. Okay. And let's over to the main screen. So this formula, we do not have to work by hand. A lot of times on the test, we've mentioned that it's just a complicated formula that you do not need to memorize. And so knowing that alone, you should be good, that this is just a complicated formula right here. If you have a sample size of UT students of 80 students, Florida students of 60 students, standard deviation for the GPA of UT students of 0.5, and standard deviation for the Florida students of 0.4. Once again, sample size group 1, sample size group 2, standard deviation of group 1, standard deviation of group 2. The degrees of freedom are 137.39. Now what we do with this is we take this and we go over here. Let's get our T applet from Mubot. This is going to tell us the shape of the t distribution. So we have to take this right here when we're doing t intervals and t tests and do the shape of the t distribution. So let's go ahead and take this. Here we go. Say hey in the chat if you want. Well, Mubot's, there we go. Mubot brought it up. And we drop it over here, and that just changes the shape of it. The t is just like the z, except the t is a much more exactly calculated distribution. If you notice right here, we don't have 1.96. We have something close to it, especially since we have a lot of degrees of freedom. The t is going to have thicker tails, as in you'll see more area in the tails, especially with lower sample sizes, more area in the tails. But as we start to increase it, it becomes more like the normal, and you see it approaching 1.96. It never truly becomes the z. It's just after so many degrees of freedom, we don't really see any differences anymore. So we have to put in our degrees of freedom, which tell us which t we are using. This is the shape of the t distribution we are using, and it's based on the degrees of freedom calculated right here. You don't need to know how to calculate it. A lot of times we've asked questions like the degrees of freedom for the two-sample t is a complicated formula we use technology to collect for. So there we go. There's the degrees of freedom. Now let's start talking about some confidence intervals. Good deal. Let's get the full screen going here. Confidence intervals. So with these confidence intervals, we have y bar. I'm going to do it in green. Really? Got to remember it goes to where the marker is on the screen. Okay. So y bar 1 minus y bar 2. That's the difference between the two sample means. Once again, we give a formula sheet. T star. I like that it did that for once. And square root s sub 1 squared over n. This is the standard error. Once again, we do give a formula sheet. There we go. So what do you have right here? Well, luckily it changed colors right in time, but this is the margin of error for the interval. The t with the star tells you that we're doing it based on a certain amount of confidence. The degrees of freedom tells you the shape of the t distribution, and right here we have the difference between the two sample means. Now, I want to point out how this all relates right here. This is the difference between sample mean 1 minus sample mean 2. And we're doing this to estimate the true difference right here. That's what we want to understand about the population. This is the parameter of interest. What is the true difference between UT students' GPAs and Florida students' GPAs? And we would take a sample of students. There'd be variation in it. We would then build a confidence interval based on a certain confidence level. And that's why the star is here. And we would get the difference plus or minus a margin of error. This is the difference between sample mean 1, UT students' GPAs, minus sample mean 2, Florida students' GPAs. And if you think about this, what if we saw something like this right here? I'm going to change colors. So with the changing of colors, what if we saw something like this right here? Well, this interval right here, try to calculate it and see if there is a difference. We have right here 3.9 minus 3.6. So this interval would end up being 0.03. Let me change that to green again. 0.3 plus or minus, and we still have that margin of error. This is just a hypothetical interval. And I want you to think about this. If you are given this interval right here, then that means the interval goes from 0.1 to 0.5. That would mean I am 95% confident the true difference between UT students and Florida students' GPAs is contained in the interval 0.1 to 0.5. Which means I think there's a difference. So here we have the margin of error of 0.2, which is about how much we could be off when we're saying what we think the difference is. Here we observed UT students had a GPA of 3.9 and Florida students had a GPA of 3.6. And then we think the true difference between all students, because remember, we just took a sample, so we're trying to estimate what the difference is. We think the true difference between all students' GPAs might be between this interval. One thing I want to point out right here is that since the difference is positive, that means we have evidence the first mean is higher. So since the interval here is positive, that's evidence that the first mean is higher because we did UT students minus Florida students when we did the difference right here. So we'll put UT right here as though this is the first mean, and Florida right here, sample mean from Florida students. Let's go ahead and look at some jump output to see how this works. We've got our, let's see if there is a difference between when it rains and demand for bikes. So here is total demand, and there's the weather. So let's go to analyze, fit y by x. We'll look right here on total demand explained by the weather. And let's go ahead and take a look. Here's the t-test right here. Okay. Woo! That's big right there. That is the difference. We're going to go ahead and look at this jump output and try to understand it. This is the 2-sample t-test jump output. And let's go ahead and look at that output. Okay, so when we have this right here, the difference, which we just saw in the formula, is going to be y bar 1 minus y bar, keep changing the wrong color, y bar 1 minus y bar 2. The standard error of the difference, I'm going to have to zoom in to write this because this one's much bigger to write. The standard error of the difference is the square root of s sub 1 squared plus s sub 2 squared over n sub 1 over n sub 2. And take a look. If you just divide these right here, you get the t ratio. To say like a divided by b, these two numbers right here is equal to c right here. So I can show this by just going right here to my calculator and typing in the following. Let's do 907.1, and we do negative, divide by, we're just going to divide by this number here, 8186.1, and look what we get right there. And if it's any decimal difference, it's just because they might carry more decimals in the background that we're not seeing. But this is, once again, the difference divided by the standard error is going to be the t statistic. The upper and lower to the interval right here is probably about 2 times the standard error, the margin of error, because this is very similar to a 95% confidence interval. So it is a 95% confidence interval, but let's take a look. 186.1 is the standard error. And remember our formula from just a moment ago was y bar 1 minus y bar 2 plus or minus, and then we have the t with degrees of freedom, and then we have the standard error, which can be abbreviated, the standard error of y bar 1 minus y bar 2. And so now when you look at this, the t a lot of times is very close to 2. We will give you t's to look for, so we will basically ask you, I can do a reverse way of calculating this, but the t is almost basically 2 for large degrees of freedom. But what if we said calculate the t right here? Well, let's take a look. Like imagine it said calculate the t statistic used to create this interval. That'd be a pretty decent question, one of the harder ones we could put on the test. Well, we know what the difference is. Let's just start plugging in numbers. The difference is going to be negative 907.1. And the standard error is right there. So the standard error is going to be 186.1. And so now we just need to find the t. So to find the t, we should be able to just divide by, and let's think right here. I think we just divide by, well, so this is, this is going to equal to this is equal to the margin of error. So my brain's just slowing down today. So this is all equal to the margin of error right here. And what we want to do now, since that is the margin of error, we want to take the margin of error and figure out margin of error, or excuse me, center of the interval plus margin of error equals upper. Like I said, this would be one of the harder questions. So since the center of the interval plus the margin of error equals the upper, we would have right here that the margin of error is what we know, that's something we don't know the number for yet. The center is 907.1 plus the margin of error, which is going to be t times 186.1 equals the upper of the interval. So negative 504, negative 540.20. And if you take a look at this right here, we can just algebra this. This turns into a big algebra problem. Like I said, this would be one of the questions I wouldn't love on the test because it's more algebra work than anything else. So we're just going to take and add this to the other side right here. The 907 will get added to the other side. So we could actually subtract their differences, or I'll do it the right way. So minus, so 540.2. There we go. And now we're going to add 907.1. And there's that. So the t times 186.1 equals 366.9. And then all we do now is we just divide by. So t is equal to 3669 divided by 186.1. And like I said, all this work to basically get, it's probably going to be, let me look at the degrees of freedom. It's probably going to be 1.972 or something. 1.972. All of that work to basically get 2. Because with enough degrees of freedom, the t will basically be 2. Or we could have just figured out what the t was by going here to the applet and putting in 205 for the degrees of freedom, putting in a p-value of 0.05, and doing the two-tailed test. So there we go right there, and there's 1.972. So all of that work right there, tons and tons of calculations to figure out something that the applet would tell us, or basically it's basically 2. As the degrees of freedom go much higher, the t statistic is basically 2. And yeah, so this right here is equal to the margin of error, all that good stuff. Understanding this output is very important. We've gone over it a good bit. Let's continue on because we've only got about 10 more minutes. That's how to read that output. Let's check this out. Okay. Degrees of freedom calculator. Here we go with the last little bit. We've done all this right here. T-test. Let's talk about the t-test some more. And setting up the null and alternative hypothesis. Okay. Okay. The t-test, is the exam going to be longer than the others? Pretty much the same amount of questions. Good questions right there, Cameron. I'm still watching the chat, so anyone, feel free to say hey or ask questions. Going to be about the same amount of questions. All that good stuff. Y bar 1 minus Y bar 2. Remember, we were just looking at this in the output a moment ago. S1 squared over N1 plus S2 squared over N2. And there's the t-test. So with this t-test right here, we're taking the difference between two means. So this is the mean for group 1 minus the mean for group 2, which is just the difference. And then we're dividing by the standard error. So we're basically standardizing the difference. We then take this t statistic and we plot it on the curve. So we go over here to the t curve with whatever the degrees of freedom are. And we plot this t statistic that we find. And then we calculate the p-value to see if we reject or fail to reject the null. Now, it's important to know when you look at this right here, the alternative hypothesis is always going to be the way that we shade. So because we're shading to the right here, we know that the alternative hypothesis, so it's right here, the null and the alternative hypothesis is going to have the greater than sign. The null always has the equal sign. When we test two means, we're talking about the true difference between mean 1 minus mean 2. So there's the true difference. That's what we're testing. And then we usually see if it's equal to 0. So that says right there, the null says that the true difference between mean 1 and mean 2 is 0. And the alternative says that the true difference between mean 1 and mean 2 is greater than 0. And when we take a look at this right here, we have a very large p-value. We could just write an estimate of it and say that the p-value right here was equal to something like 0.21. So this means we fail to reject the null right here. So test statistic calculation and interpretation. Here is the test statistic right here, and it's how many standard errors away the difference is from each other. So the further away the standard error differences are. Interpreting a hypothesis test using jump output. So one of the best things, Mubot's just talking away in the chat, is when you look at this, I like to go here to the jump output and just write mu minus mu, because you can actually see right here the null hypothesis. The null hypothesis for this question is going to be, when we think about it, the null states that mean for rain minus mean for no rain is equal to 0. The alternative, which right here we have the different signs, the alternative is either the does not equals alternative, the greater than, or the less than. So we have right here, we could pick the null for rain, or the mean for rain, minus the mean for no rain, and we could say is not equal to 0. And that's usually the one I think people miss because this is greater than absolute value of t right there. So when we look at these let us pick, and the p-values here are all very, very small. They're so small that they're basically estimating them to be 0. But knowing that you have the test right here, you're welcome, Caitlin. I hope this is helping out. I'm like, whoo, we've done a lot of information. Speedruns, please check out the other videos. If you're like, Brian, this is way too fast. These are speedruns. These are meant to be like where you see where your knowledge gaps are. These are not meant to cover every topic. check out the topic review videos or the full chapters reviews. These are like speed runs here where hopefully you're like, okay, that's this, that's this. It's how much can I cover in like 25 minutes? It's a speed run, literally. I've got the last little bit right here. Conclusion of a hypothesis test of the difference between two means. Well, we have them right here. Oh, that's awesome, Kaylin. Great work. And I'm going to hope these help people out. When we do this test right here, what would we conclude on this test? If we're testing to see if there is a difference between the two means right here. So what would you conclude looking at this p-value right here? So we state first that there is no difference between the means. We found a test statistic of basically -5. That's what's right here. The p-value is basically 0 for the does not equals alternative. And so looking at that, we would what? We would definitely reject the null. And I want you to notice something about this interval. We're testing to see if 0 is the true difference, right? That's the null hypothesis, is there's no difference between the two means. So the null is that there's no difference between the two means. And then wait a minute, when we look at the interval is completely negative. 0 is not contained in the interval. So the interval is conclusive also that we have evidence that 0 is not the true difference. So we reject that 0 is the true difference. We have evidence that 0 is not the difference. And the interval right here, the 95% confidence interval, also helps us conclude that we can reject it at the 0.05 alpha level. Whatever the confidence level here is, we can also use to do the two-tailed test. So we can reject this at the 0.05 alpha level because 0 is not contained in the interval. And I think that does it. We're going to start up the next speedrun here in a moment. So I'm going to end this video, but join the next speedrun. Check it out. We will be back here soon. Next speedrun coming up shortly. See everyone soon. Bye for now.